is it there?
Yes, sorry, I was starting the screen recording, so I haven't heard everything you have said.
Okay.
Or maybe something. I mean, the last sentence.
Yeah, it was. I didn't really open much of the busy weeks, but yeah, it's 2 weeks since I was there last time, and it's just been busy in my workplace. But on the other hand, I have read a lot of material and also the chapters. Few of the chapters until the Einstein's field equations. I don't know if they were meant to be read for this session, but I just let me reading there and have been writing some stuff in Finnish language about these theories and such.
And you've been talking about like not the Road to Reality book, right? Or Road to Reality.
Yeah, I was talking about the Road to Reality that I read the chapters 19.4, 5, and 6, I think. Yeah, but also a lot of other material. And listened all those new podcasts and YouTube videos. They especially the Brian Keating was uploading a lot of material last 2 or 3 weeks. So
what podcast?
Brian Keating.
I never heard about it.
It's the Into the Impossible podcast. Yeah, it's
Brian Keating. Has very interesting guests on.
And the very latest was with Eric Weinstein.
Yeah. Probably I've seen some links in the Portal community somewhere.
There was a look. It was concentrating to the technical matters. At least many of the questions they tried to get the technical that was handling the geometric unity topic.
Do you have a link? Maybe you can share in beta chat.
Oh yeah, I can drop it. No problem.
Yeah, thank you. So as far as I
just mention.
Yeah.
Sorry. Just gonna mention that I'm gonna attend the Epsilon group in 2 hours, just so we finish in good time.
Like you want to be at time at the Epsilon call, right?
Yeah.
Yeah, so we will try. We'll try. Anyway, I think like the main information should be covered in those like nearly 2 hours. Yeah.
So this is the last. Sorry. So you can take a look when you have a moment for it.
Yeah, I saw him somewhere. Like this Brian Keating has familiar face.
He also interviewed Penrose. Maybe you saw them.
Yeah, yes, a lot of very the geniuses.
Yeah, probably I've seen Penrose podcast with him. Okay, so let's continue talking about the progress. What about you, Alex? Alex? We don't hear you.
Okay, didn't catch that. I haven't really read anything here since last time, but I was expecting to listen in on your awesome lectures.
Yeah, okay, no problem. Yeah. And you, Joe?
Yeah, I took a look at a couple exercises, but I've mostly been reading the Griffiths electrodynamics. Yeah, I have one problem that I want to go over with that today.
You said you wanted to, right?
Yes.
Great. Okay, nice.
yeah, it's really nice that you can do that, because yeah, those problems, you're probably talking about the problems in the bottom of the pages in our book, or was it those?
Well, the one, well, yes. So I did take a look at some of the problems from the road to reality. But the problem that I want to go over is actually using the Bianchi identity to get the dual tensor from like the Maxwell tensor.
Oh, okay.
Is that the Hodge dual?
Sorry?
The dual tensor, is that the Hodge dual?
Is it still about the Hodge?
Probably not dual tensor. Probably just like two form, like standard electromagnetic tensor, like F.
Yeah. So what I'm saying is, using F and the Bianchi identity, we can get the Hodge dual of F.
Oh. Yeah, that's nice.
Mm-hmm.
Yeah, so we'll go over that.
Like Bianchi identity is actually just like exterior derivative for the two form, basically, and that's all.
Totally. Yeah, and that's how we end up getting something that's equivalent to the Hodge dual.
Interesting. Yeah. Hey Bradley, how are you?
Hey, I'm doing well. Thanks for the reminder.
Yeah, welcome. How was your progress for this week? Have you read something?
No, I haven't read anything this week.
Yeah, that's totally fine. Okay. Yeah, and as for me, I've been reading mostly like a lot of different articles. As far as I remember, I have probably 4 to show you today. Like most of them, I will just kind of review really fast. Probably just like name a few basic ideas in there, in those, and afterwards I will continue probably with the biggest one, with the colorful pictures, the one which Pugs have sent me. Anyway, I'm kind of expect that I will try to form some kind of a story basically about differential forms. Yeah, and like a slightly introduction into electromagnetic theory using differential forms, something like that. I haven't went like deep enough into that, so probably we'll take like at the 4-dimensional pictures on the next call. But anyway, like the basics, we will talk about those today. Hey, hello everyone who connected like a few seconds ago. Nate, hi, how are you? Nate, no response. Maybe Yuri, do you hear us?
Yeah, I think she said she's just listening this time.
Yeah, she said can only. Okay, and probably Nate is in kind of same situation. I see he's typing. Okay, no problem. Yeah. Mesocosmos, you wanted to say something?
Oh yes, just a simple question. You told that you can tell something about and help to realize the basic idea behind the Hodge dual. But I think for me, because probably you already talked about it last time and I wasn't here, so you don't need to repeat everything. But I just would like to know how the Hodge dual relates to Maxwell equations.
Yeah, I will show those formulas today. Yeah.
Okay, cool.
Maybe not for the electromagnetic tensor yet, but for the flux densities and field intensities, that's true. I will show those. Okay, so let's start. I see that we have enough people already. moment. Yeah, so my plan for today was to start with this article about like understanding differential forms. Please tell me if you do not see my screen currently, because it's kind of important. But anyway, for those who can only listen, for example, and not see anything, I will try to formulate myself as clear as possible. Yeah, just been looking. Don't know. Had some sounds of someone reconnecting. Anyway, I will not pay attention for now. Okay. Yeah, feel free to interrupt if you will have some questions like in the process. So this first article is basically like a math overflow answer to the question about understanding differential forms. And the main thing here is the intuition behind those. And basically we know that like using Grassmann algebras and applying those to vectors, we kind of can form n-dimensional hypervolumes. So basically we can kind of, using two vectors, we can form areas, three vectors, we can form volumes, etc. And like n-dimensional parallelotopes. And differential forms basically are the things that kind of eat n vectors, which you could think of as n-dimensional parallelotop, and it spits out a number proportional to its n-dimensional hypervolume. And it's kind of the key to the differential forms in terms of their like algebraical nature. Usually books, that's kind of really important paragraph here, I really love it. Like usually books that teach differential forms obscure this, and they will define an n form as a real-valued multilinear skew-symmetric function of n vectors. And that's exactly how like determinant is defined. And multilinearity and skew symmetry is just equals to the fact that the output of that function is proportional to length, area, volume, or basically hypervolume of our input, like as an parallelotop. And the determinant actually is the thing which is used to compute the volume of the parallelotop or parallelepiped. So it's like depends on the dimension, yeah, how we name it. Yeah, and so later it's discussed that forms, in terms of their like functional nature, like we often hear that forms could be thought of as densities, and it's kind of their characteristics, and that's needed for them, so we can kind of integrate over those. So like if you imagine that you have some kind of a curve, for example like this curve on a picture here, so just a curve, you can approximate it using like small intervals, right? Just make it not really smooth, just like a bunch of vectors there. And one-dimensional forms, they kind of the thing which will be able to measure those small how to say that? So basically we can form a line partition using those intervals or vectors. And using one form, we can fit those vectors or small parts of a line or a curve, right, to the one form, and one form will spit out the number. And after adding all of those numbers, we will be able to obtain the integral. And the magic of the one forms or any n forms is that using more like grainier partition for the curve or a surface, you will obtain like a smaller numbers, and that's why the forms are called densities. So basically it means that if you chop your surface into more fine-grained ones, you will obtain smaller results, and therefore like the sum, which equals to the integral, will converge basically. So that's like the idea behind the density thing of the n-forms. And there is one more thing to talk about here is, and that is generalized Pythagorean theorem, which is called GPT for short here. And in the same way that the squared length of an arbitrary line segment is equal to the sum of the squared lengths of its projections onto the various coordinate axes. So it means like like the length of the line segment will be equal to corresponding projections on the x, y, and z axis, for example. So it's kind of the same thing as we, for example, can see it in the vector spaces. You know, when you kind of compute the like the norm squared of the vector equals to the sum of its squared coordinates, right? So basically, its projections are the coordinates, and you need to sum all the squares and then take a square root from those. So for the like orthonormal basis, that's true, right? And we know we should use like a metric tensor in non-orthonormal cases. Yeah, but we can like go further here and expand the notion of the Pythagorean theorem to the areas, for example. So basically, we have on the picture here the like some kind of the 2D area in a 3D volume embedded in 3D space here, and this GPT theorem will tell us that like the square of that area is actually equal to the sum of its projections on different planes, and they are like xz plane here to the left, or yz plane to the right, or xy plane to the bottom. So basically we can form kind of the Pythagorean theorem for the areas, and in the same way we can form it for the volumes and hypervolumes, etc. And if you take a look at the one form now, for example, like this one, like general look, like a dx plus b dy plus c dz. So it's general look of the one form in 3D. Dx, dy, and dz are just elementary forms, and essentially they are just projectors on the corresponding coordinate axis. And you can notice that that sum is basically like the interior or dot product of the vector ABC and the vector dx, dy, dz. And in terms of the dot product, it means that it is equal to the projection of the vector ABC onto those like basic dx, dy, dz one forms, and that should be multiplied by the length of the dx, dy, dz, and the length of the dx, dy, dz is basically that square root, like square root of dx squared plus dy squared plus dz squared, and like we know from the standard calculus that that's basically the like infinitesimal density for the line length. So like it equals to the dl in the line integrals, and that means that like this sentence here is like the main thought of that paragraph. So like in other words, a dx plus b dy plus c dz is just another way of writing that projection of like project ABC onto dx, dy, dz and multiply it by the length of the line segment. So and that's kind of the old magic here. And if you move to the two forms, and you can notice that that formula for the lengths is basically the Pythagorean theorem. And if you move to the areas and area integrals, you will need like two forms, and now you can form a general two form by using a linear combination of different like projectors, different planes like dx dy, dz dx, and dy dz, right? And in the same way, you will obtain the same idea here, that you are kind of projecting the ABC onto those planes, and you are obtaining the length of that vector with double forms dx dy, dz dx, and dy dz, and that will be equal to the area of the parallelogram that
is the area of the parallelogram, is it in the above picture, is it depicted there? Is it written in the picture in the above area of the parallelogram?
Yeah, here
is it visible on that?
So probably in that case you should look on one of those pictures, like a surface and a lot of small parallelograms attached.
So the area, when you multiply with the area of the parallelogram, you mean all of those parallelograms?
Yeah, so like integral is just like a limit partitioning of the surface, right? So you kind of divide the surface into small parallelograms. And by forming parallelograms, you can feed those to the two form. And by feeding them to the two form, you kind of just calculating their areas and multiplying those by some number. And that number is will be equal to the projection of the two form coefficients, like ABC, on the basically on the plane, as far as I understand, of that parallelogram. So you kind of projecting it on the same parallelogram.
But you can't make it kind of other way around. If you have the coefficient, you can't do it backward.
If you have what?
The coefficient, when you have the generated number, it kind of loses all the information from the left side.
What number? What number? ABC?
No, the result of the equation. Let me see if there's any good example there. Like the square root, when you take the square root of all the derivatives of x, y, so you get a number from there, but from that you can't go it back to the derivate form once you have done that.
Yeah. Basically, as far as I understand, like currently under that square root are one forms, or like two forms if we are talking about the wedge product here. But after you will put into those the corresponding x and y and z vectors, sorry, not just two vectors, some kind of the two vectors like v1 and v2, which correspond to the parallelogram, like a small parallelogram of forming the partition of the surface. Then those one forms will kind of provide you with some result, or basically probably not one form but two forms. So those will be just determinants, just in areas. And that area will be equal to the projection of our original parallelogram on the xy plane. So that first dx dy wedged product is just the projection of our original parallelogram, like a small part of the surface on the xy plane. And that's the projection on the x plane. And next is for the z plane.
Okay.
Yeah, and that's kind of all for that thing. And we have one more article here, and it talks much more about like the details about n-dimensional version of the Pythagorean theorem. And at first it just talks about like the original form in 2D, like c squared equals a squared plus b squared, and we can think about those as projections of our vector v here on the I or and j axis basically, or x and y here, right? And we have the same picture here for the areas here, and basically the form of the Pythagorean theorem, you can see here it will be represented by the determinants. And that's because determinants are actually the tools to compute the volumes for any dimension. So you can use those for n dimensions and for any kind of like volume-like structures, like n vectors or n forms there. And actually it contains a really interesting section about cross products. And like we know that for like three-dimensional cross product we have that formula with determinant, right? Like ijk, and afterwards components of vector x and components of vector y in 2 rows below it, right? And by the same generalization we can form the vector product of n-1 vectors in n-dimensional space by using the determinant. And basis vectors e1, e2, en in the first row. So the idea here is the same algebraically. And by like opening that determinant, we can use like the minors here, and we will obtain some kind of the thing, you know, with like minors and plus minus sign swapping for different indices here, like for odd ones it will be plus and for even minus. Yeah, and minor is just the determinant of a smaller order, and basically just the volumes of n-1 parallelotops, and without like vector I here. So like m1 will not contain the first vector, m2 will not contain the second one, and etc, etc. So basically we're kind of considering different combinations of those cases actually, which we could see here on the picture. So basically we have n-1 volume here, and we kind of considering different projections, and that's really like really great example, because I always wanted to understand determinant in the geometrical form, and that's actually the answer. So determinant is basically about counting those projections basically. Yeah, and you can generalize the formula for the dot product with a vector product for the n space. And to dot product those, you just need to substitute the coordinates of the vector instead of the basis vector into determinant, and you will obtain something like that. And that will be n-dimensional volume. And that vector should be orthogonal to the all of those v1, v2, w and wn-1 vectors. So yeah, if it will be collinear to some of those you will obtain 0 because determinant will be equal to 0 here with two collinear rows. Yeah, and in terms of the exterior algebra, you can notice that this thing here, this vector product, is actually Hodge dual of that vector form. So basically, in terms of exterior algebra, it's about like if you have n-1 dimensional parallelotop, you can apply star operator to it, and it will return you back the vector orthogonal to that n-1 parallelotop. And that's exactly what cross product means. Yeah, and afterwards, like it follows like some kind of the proof for the n-dimensional Pythagorean theorem. I will not go into details currently, so just in terms of the ideas, that's it for like the basic notions and connection between determinants, forms, and Pythagorean theorem. Yeah. Maybe some questions? If no, I will continue.
Is the volume, the concept of volume or term of volume, is it the most general and the base term? So you can speak of one-dimensional volume, two-dimensional, three-dimensional, and so on. I'm just thinking about the length, the area, the volume, and beyond the volume. You can always talk about volumes, but
yeah, but if you have here determinant of like n by n, so just if you will take like 5 vectors here, you will obtain 5 volume.
Mm-hmm.
But you maybe not here, but probably you should take those 5 vectors here, like with that v applied. So you kind of need to convert that top formula because it's like it is a vector, not a number. So basically, to obtain the real formula, you need to apply that equation, and you kind of just need to calculate the determinant, and determinant will give you the volume with orientation. So absolute value of the determinant is the n-dimensional volume.
Mm-hmm.
And how take a look at the equation 3 here. Like equation 3 tells you how to compute it basically, because you kind of to compute your n-dimensional volume, you need to substitute in equation 3 instead of the E small here, V small, like V1 here, V2 here, and Vn here. So it will be like numbers everywhere here, and it just means that to calculate the right volume, you need to take a projection on the like n-1 vectors excluding the first one, and calculate n-1 volume of the parallelotop and multiply it by the dimension of vector like v here, v1. So you kind of take in v1 and all other dimensions for the n-1 vectors, and therefore it kind of recursively clicks, or how to say it, you know. I'm kind of starting feeling to feel that you kind of obtaining the n volumes here, and like to obtain those you need just to like calculate smaller dimensional volumes here and multiply by different coordinates of one vector, like for the fixed vector v here.
So it collects all the dimensions then?
Yeah.
Okay, from bottom to up?
From top to bottom, probably.
Does it matter in what order you do it?
Probably yes, because like I'm not sure if you can Probably it's like both direction, you know, like at first you go from top to bottom in this formula, right? Because you need to go to like to calculate n minus 1 volumes. But to calculate n minus 1 volumes, you need to calculate n minus 2. And to calculate n minus 2, you need to calculate n minus 3. And then you are going down deep to the like the lengths or areas just to the 2D volumes. And then you kind of multiply everything up back to the top and you obtain the number. So it's kind of twofold process. You have a twofold process here.
I see.
And I'm not sure about the signs here. Like there is a nice question here, like why signs should be should differ between the two consecutive components in the formula here. So like the intuition tells me that it is somehow connected with the orientation. So probably it's about like if you taking E2 here and all other vectors, then the corresponding basis will be kind of will have different chirality here, or chirality, right? Chirality. So it will be basically like left-handed.
I think one way to think about it is that the cross product is anti-symmetric. So if you have A cross B, that's the opposite of B cross A. So in order to get it to work just with these components, then basically switching any of the columns, or I guess any of the rows, would also like add a minus sign to the whole expression.
Yeah. I understand that, but I don't like algebraical explanation. Like I want to think about that geometrically somehow.
Yeah, so I think it's still okay. I guess I am thinking about it algebraically, but yeah, the way that you're thinking about it there, where you switch the chirality of it, basically, that it would just flip the orientation to switch one of the vectors in the cross product.
Yeah, so kind of I think that like if it's interesting for you, you can just take that example and maybe give it a thought on the next week. I mean, just take a 2D determinant and just explain that minus sign here, and we will have the answer.
Okay, sweet.
Anyway, let's continue, I think, and go further. Let me see if Ige increases here. No, but for him. I hope that he will be here today, because actually he was kind of the advocate of that approach described in this paper, and actually like the first time I have saw that probably this year, it was on his channel, on the YouTube channel, and he talked about like the one forms probably there, and he used the same analogy, and he also kind of wrote a few messages last week about that formulation of the one forms. I have found that article actually in the sources of the article I recommended for you to read for this week, like the article A Pictorial Introduction to Differential Geometry, and that article was in the sources, and actually I like it a lot. Like in some sense it has some really useful like information also. Anyway, let's start. So basically this article is about teaching electromagnetic field theory for undergraduate students, and the authors they put emphasis onto the usefulness of the differential forms. So basically I will try to find the nice quote here. Yeah, so they say here that like other formalisms for the electromagnetic theory are available, including bivectors, quaternions, spinors, and higher Clifford algebras. But none of these offers the combination of concrete graphical representations, ease of presentation, and close relationship to traditional vector methods that the calculus of differential forms brings to undergraduate level electromagnetics. So basically they're just saying that like exterior calculus and N forms are the most useful tool to study electromagnetic theory, and that's actually the main theme of the article. Yeah, let's take a look. One moment. So they kind of starting directly from the Maxwell Equations and some things like everything described here. So like while reading articles, I've seen those, probably on the previous call I've already said about that I've seen those strange letters like H and D. I have never seen those before. And basically because usually we are using like vector calculus, and in vector calculus they're just like scalar connected, or how to say, like they're just proportional by a scalar, and basically in like our books here we've been always using like E and B, and that's all, because H and D are kind of really connected to those two. Yeah, but anyway, you can notice here that like A, E, and H are the field intensities. And field intensities in the form notation are one forms, and flux densities, D and B, are two forms. And corresponding like current density is two form, and electric charge density is three form. And authors, they kind of just show you the table and show you the Maxwell equations here in the integral form. Yeah, so basically you can obtain the usual Maxwell equations from those integral things using Stokes' theorem basically, and putting the exterior derivative here, like transforming that integral over the line here to the integral over the area, and afterwards, like assuming that those functions are good enough, you can just remove the integrals. You obtain like partial derivative of b to the right is equal to the exterior derivative of e, and exterior derivative of one form will be curl, so it will be curl e equals to minus d by dt b, and it will be now like a familiar Maxwell equation for us. And the terms at the bottom will go to the divergence here, because b and d are two forms, and applying exterior derivative to those will give us the divergence for the certain force equation. Yeah, let's see at the picture here. So basically, afterwards, authors they start describing what is one forms using the field intensity theme, and what is two forms. So let's start. Basically, one form is like a number of surfaces perpendicular to the x-axis in that case, and that's one form, the x here. In that one form is infinite in the y and z directions, and basically like you can see that on the picture B we have one form 2dz, and you can see that they are spaced 2 per unit distance in the z direction, so basically they become denser, and probably I could say that those like one forms, they do not have like how to say that right, like a rigid structure or rigid form, you know, because you can configure that density by configuring the like how to say that, like the multitude of the form. So basically, if you assign to every surface for the dx here on the picture A some constant, for example, one surface equals to 1, then you can, by reassigning the multitude to the 1 over 2, you can just increase the density and the one form will not change. And that corresponds to adding constant 1 over 2 here before dx and putting 2 inside the x, inside the d here, basically. So you kind of could always kind of make something denser, make the form denser by decreasing its multitude. That's the basic idea. And a general one form will have the curved surfaces, not those clean and nice planes as for the dx or 2dz from on the pictures A and B. And a general one form with curved surfaces will look something like that, and those surfaces could end somewhere or meet each other, and that's like totally okay. Also, nice comment for that section is that differential forms, in that terms like one forms, they lead to the energy picture of the field intensity, and basically like the usual physical motivation for the electric field intensity is the force experienced by a small test charge placed in the field. So like field intensities are about like a force picture. And another physical viewpoint for the electric field is the change in the potential experienced by a charge as it moves through the field. And this leads naturally to the equipotential representation of the field. And that's the same picture we have seen like in the chapter 10 of the Penrose book, when we have seen that gradient maps, like contour maps of the surfaces, you know. So basically those one forms, they are those equipotential representation of the fields. And that's the reason why we can think about field intensities in terms of the equipotential representation of the field, like magnetic or electric field, E or H here. Yeah, and if we move one more moment here, we can form the dual of the one form by just using its coefficients E1, E2, E3 with the basis vectors like this x hat, y hat, and z hat. And as far as I understand, I'm not sure here, but I think that corresponds to the index lowering, or sorry, index uppering, how to say that correctly. So basically just a metric tensor acting on that one form here. Yeah, and if you go to the two forms, those will describe flux densities and current density. And those two forms can be understood in terms of like a mesh or a grid formed by the intersection of two one forms. So basically dx dy will look something like that. Take a look at the picture on the right, picture A. The two form dx dy are just those tubes in the z direction here. So you kind of have two sets of the planes here. One is corresponding to the dx, perpendicular here to the x-axis, and the other for the y-axis. And therefore, dx dy just means those tubes into the z direction. And on the another picture, you can see that like those tubes could have like how to say that, like a more general form. They shouldn't be like a straight tubes, and that's so they could be curved somehow, twisted, and that's okay. And in that case, you can see here that, to be precise, the tubes of the two forms, they have no definite shape. Tubes of dx dy have the same density as of those, like if you, for example, make one like dy form denser and x form, like you will halve the density of the x forms and double the density of the y forms. You will obtain the same dx dy form. So basically it worries only about the density of the area there. Yeah, I'm not sure about that picture. Let's take a look also at the picture on the left. So on the left we have a pass piercing four surfaces of a one form, and the integral of the one form over the pass is 4. And it means that the magnitude for every surface of the one form equals to 1 in that case. So you should have like properly normalized form for that occasion. So and there could be a case if for every surface the different number is assigned, and you can just summing up those assigned numbers there. Yeah, so like flux densities D and B, so like B is a flux density for the magnetic field and D is a flux density for the electric field. They could be understood in terms of the two forms, so they are tubes, and also current. It is also a two form, and which correspond also to some kind of the tubes in the space, in the 3D space, and you can form also those dual vectors to the two forms the same way they were formed for the one forms. So just take the components and place the coordinate vectors there. Yeah, and if you come to the three forms, like charge density, here it says that like some scalar physical quantities are densities and can be integrated over a volume in 3D, right? And for other scalar quantities, such as electric potential, a volume integral make no sense. And the calculus of forms distinguishes like explicitly between these two types of quantities by representing densities as three forms. So volume charge density, for example, becomes this thing, like R equals Q by dx dy dz. And in terms of the pictures, we can understand that as like one more intersection of our tubes by the planes perpendicular to the axis, and therefore we will obtain those small volumes here and like cubes. So basically we will have those small cubes, and if you will integrate that form, you just need to take like some volume and count the number of cubes inside of it. Yeah, and basically like that's all about like 1, 2, and 3 forms. And now we can interpret our Maxwell laws in terms of the form language. So we can take like the Ampere's and Faraday's law. Faraday's law is the first here, and Ampere's law is the second one. Like first says that like circulation of the electric field is equal to the change of the magnetic flux through some surface here, A, and circulation of the field intensity of the magnetic field equals to the change of the flux of electric field and also currents flowing through the surface. Yeah, and now we can picture those, and you can see a picture for the Ampere's law here on the left. So a graphical representation of the Ampere's laws could look like that. You can see like the tubes of current produce surfaces of magnetic field intensity, and any loop around the 3 tubes of our current must pierce 3 surfaces of H exactly, and therefore the integrals will be the same there. So that's kind of the pictorial representation of the curl. And you can see on the picture B that a cross-section of the same magnetic field, that's a cross-section of the same magnetic field using vectors. And the vector field appears to curl everywhere, even though the field has non-zero curl only at the location of the current. Yeah, that's kind of a bit non-intuitive here, and it's a bit explained in that article. So basically curl is non-zero at that point, but like vector field here curls. Probably, yeah, I'm not understanding that picture good enough, but what authors have been saying in the articles, I said that this picture is actually counterintuitive, and it's better to think in terms of the 1 forms and 2 forms as on the picture right here. Yeah, and like the same way you can add the tubes of the flux density here, I think. Not sure about how we can interpret the time change, but like we should skip that for today. Anyway, and if you come to the divergence things like Gauss law, then you can represent it in terms of the 3 forms generating 2 forms. And you can see that the boxes of R here, they produce tubes of D. So basically charges, they produce the electric flux density here. Yeah, and here we come to the Hodge duals actually, and like in the usual vector calculus we have the vector expressions for the constitutive relations for an isotropic medium, and they are like D equals epsilon E and B equals mu H. But in a world of forms we cannot just multiply those, because D and B are 2 forms while E and H are just 1 forms. So we need some kind of the instrument, an operator that will relate those forms of different degrees. And the Hodge star operator is exactly the tool to be used here. And in the Euclidean space, it will just kind of complement. It will act like an orthogonal complement, and that's all, without even changing the orientation here. So basically, star of dx is dy dz, and the same way for the dy and dz. And 0 and 3 forms will be related as like star of 1 equals to dx dy dz. Double star will be equal to alpha, and 1 form w or omega is dual to the same vector as the 2 form star w. So in terms of components, there's the same actually. So using the star operator, we can rewrite or rewrote those constitutive relations into those, like D will be equal epsilon star E, and B will be equal to mu star H. So basically you can see on the figure 7 how we could obtain flux densities or field intensities by using star operator. So if you apply star operator to those tubes, you will obtain field intensities, those perpendicular 1 forms to the surfaces. And if you apply star operator to these planes here, 1 form, you will obtain the flux tubes. So basically that's like taking the orthogonal complement in the standard Euclidean coordinates. Yeah, and there is an example of calculating like directly using some algebra, like if you have some field intensity, how to calculate flux density. Yeah, I will skip it. There is also some theory about exterior product and some examples of, I don't know, point in power. I'm not aware about it like too much, so some talk about the energy actually. And you can see the familiar thing for the 3D volumes here in terms of the vector products, and those all are just special cases of the wedge products here, which kind of could be thought of as determinants basically. I mean, if you add the determinant to those, you will calculate the corresponding volumes here. So those are just like 3 parallel tops. Yeah, and after like showing a few examples here, authors talk about curvilinear coordinate systems, and it's also interesting because like in curvilinear coordinate systems, for example in cylindrical coordinates, the look of the general one form will differ because you will have like different densities. For example, for dphi you will have additional rho here, and it will be dual to the vector like that, like a rho hat, b phi hat, and c v hat. And the general 2 form will now look like this. Also notice that we have additional r in the 2 forms where dphi is. And therefore the Hodge duals will also differ a bit because you will need to, for example, multiply dphi by rho here for 1 over rho not to appear on the right. And you will have 2 additional rhos for every dphi in the Hodge dual. So you kind of need not to forget about those things. So basically the volume element of those things will be equal to the r d rho dphi dz, and as with rectangular coordinates, double star will be equal to 1. Yeah, so if you apply the star operator to dphi dz, you will obtain 1 over r dr. Yeah, and now let's go to the pictures. So if you take a look at the pictures, you will see that one forms, and in the curvilinear coordinates they will look differently, and basically those are kind of parallel to the coordinate lines, right? So on the first picture we have dr, and you can see those concentric cylinders in 3D or circles in 2D. And for the dphi you will have those rotating planes there. And for dz, we will have the same form we have had in the Cartesian coordinates there. Yeah, and also we have, as example here, also spherical coordinates, where we have the inclination, theta angle from 0 to 180 degrees, and polar angle dphi with a whole turn. And in polar coordinates, you can see that the surfaces would look differently because now dr is the radius of a sphere here, so we will have a concentric spheres, not cylinders. For z we will have like the same one form as for the dphi. I mean for dphi it will be the same as the dphi in the cylindrical coordinates. And for the inclination, for the d theta, we will have those concentric like conuses there. Yeah, and now we can kind of move into those coordinates. We can rewrite a bit our Gauss law, for example, and think about that into spherical and more symmetrical terms. And that could be seen on the picture here on the right, figure 12, that those small cubes will kind of project the flux densities into like a spherical space, so we'll have a spherical symmetry, and therefore we will obtain that 4 pi coefficient for the electrical flux density here. Yeah, there are some also like different examples, like if you have some line charge like going through some fiber here, and then you will have like tubes of D extended radially away from the vertical line of charge, and magnetic field intensity due to the line current will look like that. Yeah, and afterwards authors talk about exterior derivatives. So basically like that one form with gradient multiplied by the dx dy dz here. So it could be called gradient also. Yeah, and we can calculate our electric field here, like one form from the scalar potential, which is zero form, just a scalar field, using that equation. So basically it's just a gradient of phi with a minus sign here. And we can go further and calculate, for example, the next exterior derivative, and you can see the explicit formula written here. So basically to take the exterior derivative, you need to take partial derivatives of every one form here, like coefficients to the one form here, and wedge product everything, like dx with dx, dy with dx, dz with dx, and etc. And therefore, using like the wedge relations, we know that dx will have the zero area, and therefore it will go to zero, and only dy dx and dz dx will be left from the first constituent of that equation. Yeah, anyway, we'll obtain the curl here actually, and yeah, there is also a note that if exterior derivative is equal to zero, the form is called closed, and it represents a conservative field. And basically it means that like no surfaces of the form will intersect, so they will be closed. Yeah, and that's actually what is said next. Like surfaces representing different potential values can never meet. That's what mean for the field to be conservative. And if exterior derivative doesn't equal zero, the field is non-conservative, and surfaces meet or end wherever the exterior derivative is non-zero. So you can take one more exterior derivative in 3D and obtain divergence here for the dB, for example, for the two form, right? Yeah, there are like in the next paragraph they talk about some properties of the exterior derivation, like d squared equals zero, and that how to say that, like product rule formula here. Yeah, and basically they go to the Stokes generalized Stokes theorem, which we already seen, and it kind of represent the fundamental theorem of calculus and like divergence theorem, and we have nice pictures here for those. So like Stokes theorem for the one form A, on the A we can see a loop. We can name that like circle M, and the loop is a boundary, so BD here means boundary of M, right? So, and we can see that the number of surfaces it pierces here equals to 3. And in terms of the Stokes theorem, it means that if you take the exterior derivative of that form, you will obtain some tubes, and exactly 3 tubes will go through the area, through the circle of like through the M, and that's a case of the Stokes theorem for a one form. And for two forms, you can see here that we have some 2D surface, like a box here, and some flux density going on, like two form, so those tubes. And Stokes theorem in that case tells us that we can also take like this free form, the exterior derivative of that flux, and we know that the same number of boxes of the 3 form will lie inside this surface. Yeah, so basically that's it. I think that like everything else we can just postpone, because like we have here the derivation of the point form, which I have already said about, just deriving the standard Maxwell equation from the integral form. There is also an interesting notion of the pullback and interior product, but I think we shouldn't talk about those today. Yeah, and I propose to to switch to the jaw presentation from the Griffiths book, because we don't have like a lot of time left. Yeah, and after it we will see. Like probably I think we should talk about that paper next time, the final one. Yeah, any questions?
It takes a little bit time to digest everything that was on this paper. I was just wondering, what are the about the electromagnetic field there? What are the general concept or basic concepts you should know from the theory? So in this paper, there were the theory was explained with the differential forms, but is there any way to say from what parts the electromagnetic field theory come from, or consists?
So as far as I understood it, your question is why the exact physical things like electric field are one forms.
No.
Or what?
Yeah, it was a more general question, just trying to grasp the idea of the electromagnetic field theory itself. So if you would need to put it on 3 parts and say what is the theory actually, is there any way to say it in a concise way?
Like you want to derive it somehow?
Not just a definition or something like that.
Yeah, but basically it kind of self-describing by the Maxwell laws, I think, and Lorentz force. So that's basically all. You kind of put your charges and currents into the space, and they form out the fields around those, and those fields interact with particles having charges and currents, right? So basically it's just like field-particle interactions using the Maxwell equations and Lorentz force law, and it's all.
Okay, and that's it.
So yeah, I think the different view of the electromagnetic theory is from the perspective of the theoretical mechanics or physics. I don't know, like classical field theory. I mean, in terms of the Lagrangian, for example, right, and electromagnetic potential, and like using special relativity to merge everything into the 4-vector charge current 4-vector there. And have a 4-vector for the electromagnetic potential, and afterwards take the anti-symmetric form of it. Probably it will be like a exterior derivative of that one form. Probably it will be one form, and you will obtain electromagnetic tensor like the F there. And you can build a Lagrangian, and probably we should talk about that in the chapter 20. I think that would be more appropriate, like that Lagrangian formalism.
Okay, I think this was enough.
Yeah. So basically, it's, as far as I understand it, it's just Maxwell laws and Lorentz force law, and that's all. And you kind of have space, have your particles, have your fields, and that's the same as with the gravitation. like mass curves space-time, and space-time tells mass how to move, and that's exactly the same thing with the electromagnetic field. So like electromagnetic field tells charges how to move, and they tell the field how to be modified, basically.
Okay, actually, sorry, I'm at the voice at the moment, but because the picture here is it relates to the question I asked a little bit earlier. The region of integration, point, path, surface, volume. This was actually what I was referring with my question. What is the 4 form and 5 form and so far? Do they have any concepts beyond the volume? Or just they should be called like 4 form, 5 form, 6 form, and so forth?
Well, I think you can just call it a hypervolume, because it still has like similar properties to the volume, just higher dimension.
Yeah, you know, basically volumes, they are like determinants. So determinants are volumes, are oriented volumes, basically. But like if you take n vector, like a wedge product of n vectors, you will obtain n-dimensional parallelotope. And n-dimensional parallelotope, you can think about that in terms of volume, right? If you apply the determinant to it. And n form, in that case, will be like a dual to that n vector. You can kind of dualize it. And like n form is actually the density. If I may refer to the first article here, so like n form will accept as the input the n parallelotope, so n vectors, and will spit you out the number which will be proportional to the volume of the parallelotope, and that's it. And that's why we call n forms densities. So basically n forms are actually densities. They are some functions proportional to the n-dimensional hypervolumes.
I see. Yeah, this is what I was looking for. Yes.
Yeah. So n vectors, they are parallelotopes. N forms, they are densities, which are kind of functions which will be proportional to the volume of the n parallelotope.
Yes, great. It's quite fascinating that the Pythagorean theorem it works from any dimensions.
I never imagined that stuff before.
Yeah, it's
yeah, that's true. That's impressive. Yeah. Sorry. So probably we should shift to the Joe's talk, right? Joe, are you ready?
Yeah.
Okay, so let's go. I will stop my sharing.
Okay, can you guys see my screen?
Yeah.
Okay, so what I have written here are two things that we're going to start out with, and this first one is a definition of the electromagnetic field tensor, and it's written in terms of this potential. So this potential, I can write it down here. A mu is going to be like the scalar potential and the vector potential. So, you know, the scalar potential, this is what you'd have, like, you know, the electric field is, you know, the gradient of this scalar. And this one here, the magnetic field, is the curl of this vector potential. So this is going to be our starting point. Is this an okay starting point, or should I talk a little bit more about the potential?
At least for me, it would be great to have a little bit more. I don't know about others.
Yeah, and John, maybe you can say like a few words, like basic information, like what is a potential? So, like in terms of physician.
Okay, so like a potential is it tells you like the sort of energy landscape that a particle has access to. So like, you know, for a simple demonstration of a potential, we could talk about you know, projectile motion. So the potential for gravity, we'll write it as V. The potential would increase as you increase in height. So like, you know, mgz sort of thing. So this is for a projectile motion problem where you have something like that. You know, you throw an object from the origin, and the whole time that it's flying, there's like this downward force, and that's that downward force is gravity. Right. So everywhere along the curve, there's just a downward force. So as you're at the peak of the curve, the potential should be a maximum. And when you're at the bottom of the curve, the potential should be a minimum. So I actually just chose this function. Like if this is, you know, if this axis is z, I just chose this function so that, you know, as z increases, the potential goes higher. Mm-hmm. So Newton tells us that that we can find the force from this potential using the gradient. So the gradient of this thing is just a minus mg in the z direction. But this is like the good old thing that that, you know, we're familiar with in projectile motion problems is like, you know, F equals ma, and a is just, you know, the gravitational acceleration in the minus z direction. So so this is what I mean when I say like a potential. It's it sort of tells you about like the energy landscape, and Newton tells us how to get the forces from this energy landscape. Are there any questions on this part?
This is good.
Okay. So the interesting thing is this is just a scalar potential, so we can take a gradient to get the force, because the force is a vector quantity. So if we were to have some sort of vector potential like a, you know, it's a1, a2, a3, and we wanted to get some vector quantity for force, well, the interesting thing is that we would actually, you know, we can't just do the gradient of a vector. There's like a few options that you could do, and those options are either divergence or curl.
Yeah, so basically it's kind of brute force in exterior derivatives there.
Precisely, yeah. So it's just like you have a couple of options, and it turns out like if you want to do the total derivative, then you just like, you know, add all the options. Del dot a, but this would be like in the r hat direction. So this r hat would be like a, you know, dx wedge dy wedge dz, or whatever the components are, depending on what r is. So this is just a little preamble for potentials. It's just saying that, you know, if you want to get a vector quantity that represents some of the like physics about what you're talking about, you can do this in terms of the potentials, and it's usually in terms of like the derivatives of the potential. And it's the same case for scalars and vector potentials. It's just that, you know, if we want to get some physical quantity that represents the motion of the system, or the state of the system, we can do this in terms of the derivatives of the potential. So now, with that little background on potentials, I'm going to talk about the electromagnetic 4 potential. So this is a 4 vector where the first component will be a scalar potential, and the other components will be a vector potential. And the interesting thing is, like, if we look at Gauss's law, del dot E equals rho over epsilon. If we look at Gauss's law and we write the electric field as the gradient of this scalar, then we have del dot the gradient of phi equals rho over epsilon naught. And we can simplify this to just be the Laplacian of phi equals rho over epsilon naught. And this is actually a important equation, the Poisson equation. I'm not looking to get into this too much right now, but what I wanted to show you is that, like, by taking derivatives of this potential, you know, see, we take the, I'll change color. If we take the scalar component and we take a derivative of that to get some field, this actually, like, satisfies Maxwell's equations. And so what we get out of this is being able to put Maxwell's equations in terms of these potentials. So you can see, like, you know, since Gauss's law is a scalar equation, it's the you know, divergence of the electric field. Since it's a scalar equation, we're going to use the scalar potential. But for vector equations, like so for vector equations like Ampere's law, okay, so we have Ampere's law. We can write this in terms of the potentials. It would be like the curl of the curl of A equals naught J plus the time derivative of the gradient of phi. So I know that this is kind of a lot to work with, but what I'm really trying to show here is that you can do manipulations on this vector potential to actually get Maxwell's equations. And so this is going to be kind of the starting point for the derivation that I want to do. Is there any questions about this? I don't think that we'll heavily rely on getting Maxwell's equations from the vector potential here. We're mostly going to do manipulations on the field tensor, but just in terms of starting with some potential and ending up with equations of motion, does this idea make sense in the same way that the projectile motion did?
Yeah. I also thought about, like, the divergence of the B here, and it seems like we will obtain, like, in that case, divergence of the curl, right? And it's like d squared, so we will obtain 0 automatically.
Exactly. Yep. The divergence of the curl will always be 0, and that is that boundary of the boundary equation.
Yeah, so basic picture is like this. Like, we have electric force and a magnetic force, basically, and they are kind of proportional to the E and B, and E and B could be defined using potentials. So that's kind of the link between potentials and the forces, as far as I understand that.
Yeah, exactly. And the sort of like exact link that we'll use is that the fields can be written in terms of derivatives of these potentials. You have to do a gradient if it's the scalar potential, and you have to do like a curl if it's the vector potential.
Can you get Maxwell from the scalar potential, not only vector?
What's the question? Sorry. Can you get Maxwell's equations from?
Yeah, from the scalar potential. You mentioned, if I recall right, that you are going to present the Maxwell equations from vector potential, right?
Well, so the derivation that I want to do is from the Bianchi identity. I want to find out what the Hodge dual of the electromagnetic tensor is. So like as a quick sketch of what I'm going to do, it's like the Bianchi identity looks like this. And these brackets are for the anti-symmetrized thing, like the same way that that Penrose would write it.
Yeah, so basically it's just df, like exterior derivative of f equals 0.
Yeah, exactly. So this was like the first Maxwell equation that was written in, I think it's 19.3. So starting here, what we're going to end up with is actually showing that let's see, I think we show the d lambda, I can do a star f sub alpha lambda equals 0. Just as a quick sketch of what we're going to do, we're going to start with this Bianchi identity, and then we're going to end up with the Hodge dual of f.
Okay.
And so sadly for Slava, it's going to be an algebraic derivation.
Maybe I will interpret it geometrically for the next time.
Oh, yeah.
About one, it's maybe a side question, but you mentioned about Poisson equation. Is it related to the Poisson distribution? Anyhow.
Now, so these guys are really big in math, and they did a whole lot of stuff. So it is. I think it is the same Poisson, but I don't think it's like a related topic.
All right. Yeah, possibly.
I also have one more question. Like, why we cannot use a scalar potential for the B, and we are using some kind of the vector potential there?
Oh well, it's just because so here, let's see. I'll make some more space. So we had the 4 Maxwell equations, del dot E rho epsilon, del dot B equals 0. I'm going to be off by some constants here.
Yeah, okay.
Okay, so this is our Maxwell equations. And the reason why we can't write B in terms of like, so if we had B equals the gradient of a scalar, I can rewrite that. If B equals the gradient of a scalar, then what we'd end up with is that del squared of that scalar equals 0. But the same thing happens as up here. It's like, well, that only works for when the charge densities are 0. So what we mean when we like say, oh, you can't you can't do this. The reason why is because there's no magnetic monopoles. So this charge distribution here would be 0 always. And one way to represent that is by picking B to be the curl of some vector.
Yeah, but
and this is
why we cannot use some other potential, like special magnetic potential, like phi2, for example, and that will correspond to the magnetic charges or something like that?
Well, this is an interesting question, because like we basically know Maxwell's equations before we assign these potentials. So like you know, this is kind of a thing that like lazy physicists do when they have something that they know that works and they want to get it into a form that they can do more manipulations with. They basically construct it so that it'll just give you back the same form that we've got. So, in the case that that the like Laplacian of your scalar, I can erase this. In this case on the right, where the Laplacian of the scalar potential is 0, there's like similar to the Poisson equation that we saw before. This is Laplace's equation.
Like just the sum of the second derivatives, right?
Yeah. Yeah, and it turns out that to say Laplace's equation, there's some property. It has to do with line integrals and closed loop integrals. If you do a closed loop integral, it's got to work out nicely and satisfy Stokes' equation and stuff like that. So what happens is, if you write B as the gradient of some scalar, it doesn't satisfy all of the Maxwell equations. Oh, well, I can actually see it already. So what's the curl of the gradient?
Yeah.
Like the fourth
yeah,
Maxwell equation.
0.
Yeah, so that's already it. You know, you
Yeah,
can do like a line integral form of this. But
Yeah, and I think that the main source of confusion here is vectors, actually. So if you think about those like forms, then you will not be confused, because like to obtain a 2 form, you will need to apply a curl to the 1 form.
yeah, totally. So it's all about just kind of making it work, because like these two statements are incompatible.
Yeah, true. Now I see it too, yeah.
Okay, these are good questions, and I think it helps to build the background for the derivation we're about to do. Are there any other questions? Okay, great. So I'll just write down what we've got again. So we've got this vector potential that we wrote, and it's in terms of the scalar potential, which gives you like the electric fields, and the 3 vector potential, which gives you the magnetic fields. And so I'm going to start from the definition of the Maxwell tensor. So I'll do 3 equals for a definition. And it looks like a 4-dimensional curl. So we'll take a derivative of A, and we'll swap the indices and do a similar looking term. So this is the definition of the Maxwell tensor in terms of these scalar, or in terms of the vector potential. So you could see here that if we were to switch, like, you know, if we were to calculate what F nu mu is, well, you'd just get a minus sign. So F is totally anti-symmetric. And we're actually going to use that a little bit.
Yeah, so basically here we have like, it seems to me, it's like we have like 2-1 forms, and we are wedging those, like making anti-symmetric relation between those. So it's like 2 multiplied by like d wedge a.
Yep, exactly. F tensor, I'll write it like that. F tensor is 2 dA. Like if the lowercase d is the exterior derivative.
Ah, okay, so it's, got it.
So I think I'm going to leave it in the component notation, just because that ends up how we do this. That ends up working out for this derivation. So these are all our givens up top here, and we have one more given, and that's the Bianchi identity. So we're going to say like derivatives with respect to the components. So this last equation that I wrote here is the Bianchi identity.
Can you spell and write down the Bianchi? How is it written? Bianchi. Okay, thanks.
Yeah, no problem.
Yeah, John, now I see that in terms of the exterior calculus, it's kind of trivial identity because you kind of taken double exterior derivative, like d from 2dA.
Exactly. Yeah, it's yet again, it's boundary of a boundary.
Yeah.
So so we can actually write out what all these terms are, and when we do this, Penrose defines it somewhere, but it's basically we just take symmetric and anti-symmetric permutations of it. So I'll take the first term as just d lambda f mu nu, and then I'm going to permute it. So I'm going to start with mu on the next term. So d mu f nu lambda. And then we're going to start with nu, nu f sub nu mu. Oh wait, is that? No, that's not right.
Yeah, actually here you need to include everything. I mean like all permutations with plus and minus signs here, and afterwards kind of use the anti-symmetry property of the F tensor. So you'll kind of how to say it, merge like 3 by 3, or how to say it correctly, like merge those into pairs.
Yeah, exactly. So when we write this out, these are the 3 even permutations, and then now we have 3 odd permutations.
Yeah.
Okay, so this is just expanding the Bianchi identity. And then as Slava suggested, we're going to use this anti-symmetry property because this term with the minus sign is actually the same thing as this term here. So you can see we can just say like, oh, if we have mu and lambda here, and lambda and mu here, we can just switch the sign on this term. So what we actually end up with is just 2 times the first 3 terms that we've got. Everyone follow this step? We just use the anti-symmetry of the tensor.
Yes, quite clear.
Okay, great. So now we have this factor of 2, and we can get rid of it. Just divide both sides of the equation by 2. So just rewrite it for clarity. So this is what we're working with now. And from here, I'm going to actually substitute in the definition for each of these terms. So you can see this first one that we've got, f mu nu. This is like actually what I wrote up here. So I'll just substitute each of these in. Is it okay if I scroll down, or should I try to zoom out?
Yeah, I think that's okay.
So, you know, each of these f terms is just like mixed derivatives of a. So we'll have d lambda, d mu a nu, minus d nu a mu, plus d mu, d nu a lambda, minus d lambda a nu, plus d nu f, oh wait, d lambda a mu minus d mu a lambda equals 0. So now what I'm going to do is I'm going to group these in terms of the components of A. So we have an A nu here, we have an A nu here. I'll use 3 different colors. We have A mu here, and A mu here. And then we have A lambda here, and A lambda here. Oh wait, that's wrong. A lambda here. So you can see we've got like 2 for each term.
Mm-hmm.
So I'm gonna group everything. And what we end up with is, like, for this first one we get d lambda d mu. And the other A nu term is a minus d mu d lambda A nu. And the next term is going to be for the nu and lambda terms. And then the next term will be for mu and nu. Okay, so I know that this is a lot of manipulation here already, but can everyone tell where, like, how we got here just from, you know, perhaps this equation? Maybe a better way to say it is, does anyone have any questions right here?
Have you seen the questions on the text chat?
I have not. Thank you.
On the comments.
I'm being a bit pedantic. For non-static cases, there's a time term. Yeah, totally. Oh yeah. So, Yuri, to answer your question, for the advantage of using the potential formulation is, like, for your degrees of freedom in the Maxwell equation, you have 6 of them. You have E1, E2, E3, you have B1, B2, B3. That's like in the fields formulation. But in the potential formulation, you just have phi, A1, A2, A3. So it actually reduces the number of degrees of freedom. But there's kind of an exchange with it. Like, when you try to get rid of degrees of freedom, what you end up with is having to make some choices. And those choices that you make, it's a really deep point. But the choices that you have to make to deal with this like decrease in the number of degrees of freedom, that's actually what gives you gauge freedom in Maxwell's equations. So I think this, this is a whole tangent that I would like to go on, but perhaps let's finish the derivation, and because I think other people have things to present as well. Maybe I can talk about this next week or something. But definitely, that is a great question, Yuri. The answer is that reducing the number of degrees of freedom actually gives you freedom to select a gauge. And so it's the way to formulate the gauge invariant Maxwell equations. And ultimately, it's easier because you have only 4 degrees of freedom instead of 6.
Yeah, actually in 4 minutes, like epsilon group is starting. So, for example, Alex will go there, and I assume we should continue.
Okay. Yeah. So I'm almost done with the derivation. Actually, I just want to make sure that everybody is up to speed with the spot that we got to. We started with the Bianchi identity. Sorry?
Actually, you can continue if you like, however long. I can listen to the recording later.
Okay, sweet.
Oh, yeah, that's true.
Cool. So this part that we got to, we started with the Bianchi identity, expanded it out, did some simplification using the anti-symmetry, and then we expanded it out again in terms of the F mu nu. And then, so this is the expression that we end up with. And I wanted to point out that if any of these indices are matching, then we'll get terms that are all 0. So it's kind of a wild thing to notice. But if, like, say lambda and mu are equal to each other, then this first term is 0. And the other 2 terms will cancel each other out. So from this, we know that mu, or I guess lambda, mu, and nu are distinct. If we want anything that's like meaningful, because if they're not, then you just get something like 0 equals 0, and that's not very fun. So another thing to notice is, we use the permutations when we like calculated this Bianchi identity. We used the permutations. So like it would be helpful to look for something that looks like a Levi-Civita symbol. So I'll say this looks like Levi-Civita. And the way that it looks like Levi-Civita is if we're taking a derivative with respect to a particular component, then there will be a plus or minus sign on that component depending on the order of lambda, mu, and nu. This isn't a complete expression here, but do you see how, like, I'll highlight this and this? You see how this would be like an even permutation, so it ends up positive? Maybe I should continue writing it out. So each of these terms, they look like this. So this is kind of a nasty thing, but it turns out that if you do all of the contractions on each of these indices, you have basically the only index that's left over after all the contractions is just lambda. Because you contract on A, you contract on mu, and you contract on nu. But interestingly enough, this term in parentheses here, this is just the field tensor. So I'll rewrite this expression. And so we are almost there. The last thing to consider is that we had a factor of 2 in the beginning, and we want to be consistent. So when we define this thing, it's easy to just take the whole equation and just multiply it by 1/2 because of the 0 on this side. So this will be the same equation as d alpha is 1/2. And we have epsilon alpha lambda mu nu contracted with our field tensor, and we get 0. But if we look at our homogeneous version of Maxwell's equations, what they end up with is something that looks exactly like this. So we can actually call this star f. Alpha lambda. Oh wait, I think it's actually upper alpha lambda. And so what we find is that star f alpha lambda is equal to 1/2 Levi-Civita, and then the lower index. So this is a big deal, is that just from the Bianchi identity, we were able to find out the exact expression for the Hodge dual of the electromagnetic tensor. So that concludes the derivation.
So what does it mean then? What does it tell about the Bianchi equation? What is the relation?
Well, so I'm kind of working this backwards from how most people work it out. It's like using the dual or something to show that the electromagnetic tensor satisfies the Bianchi identity. But the reason that I thought about it this way was because last week we were, actually I guess for the previous few weeks, we were concerned with how to actually evaluate the Hodge dual. And so I kind of inverted this problem where usually you start with the dual and prove the Bianchi identity. But I just inverted that and say, starting with the Bianchi identity, what is the dual of the electromagnetic tensor? Does that answer your question?
It gives us some sort of answer. I was just thinking about the Bianchi identity. What is the, if you think it as alone, what is
so Bianchi identity is just like two Maxwell equations compacted together. So it's like homogeneous Maxwell equations, basically.
Okay. And from those two, you can derive a Hodge dual, or actually using that identity.
Yeah, exactly. So what I ended up with here was the exact form of the Hodge dual that Penrose writes down.
Yeah, I have a question. Could you scroll a little bit up? like maybe 2 lines. Yeah. So, oh, and one more. Maybe here. Yeah, I'm just not sure I understood why did we need to expand everything to obtain the Hodge dual? Like, if you expand everything and regroup, then you will notice. I'm just don't understand like those mixed derivatives there, like that line with like d lambda d mu and minus d mu d lambda in the brackets. It's like 0 for me, right?
The first term is 0. Is that what you're saying?
Yeah, like the first, the second one, and the third. If there is no curvature, then our second derivatives are all zeros, right? So it's kind of proof of the Bianchi identity.
Yeah, so I see what you're saying. Like the idea, I mean, Penrose would tell you that you're done here. You just write this down and you don't need to worry about the derivation.
Yeah.
But, I just wanted to be very explicit in the derivation. So I expanded everything out, and then I showed where the Levi-Civita tensor comes from. It comes from the anti-symmetry of these 3 indices. So like, Penrose just writes down this equation. He just says, okay, the Hodge dual is in terms of, the raised Levi-Civita tensor. And I think he even writes something like, you have to do a metric to raise each of those indices. So you have like 1/2, and you have like eta, alpha, rho, eta, lambda, sigma, eta, mu, chi, eta, nu, xi. And then you'd have the lowered version, and this would be, oh, wait. Is this right? What am I doing? No, these all need to be upper indices. That's what I'm doing. Sigma, chi, xi.
Yeah, so he has actually like the lower indexed Hodge dual there. So you obtain the Hodge dual of the 2 vector there, and you need to obtain Hodge dual of the 2 form. So and if you want to do that, you need to swap your Levi-Civita to the lower version and your 2 form to 2 vector using metric tensor.
I see. So yeah, we just have a bunch of metrics in here. I wrote out 4 of them to raise the Levi-Civita. But I thought that this form that I have boxed here, I thought that was like descriptive. I could tell what the components are, but I didn't really understand like why it had to be of that form. So the solution that I came up to this question was that you can actually get it directly from the Bianchi identity.
Could you explain like one more time about this Levi-Civita symbol, like how you derived it? From what equation? So from the last one with a's, this one with the mixed derivatives?
Yeah, so I was just saying like if, like the first one here is lambda, mu, and then nu. And that's like a positive term. Oh, oops. And then the mu, lambda, nu is just like switching one of those. So what we have is something where if you have like a cyclic permutation, then it ends up positive. and if it's an anti-cyclic permutation, then it ends up negative.
Yeah. So you kind of can just represent those indices on a circle, and if it's going like clockwise or anti-clockwise.
Yeah, exactly. So that's how we came up with Levi-Civita. Basically, the contraction of this alpha with this alpha, it just gives you the appropriate minus signs in the expression. And then the lambda, mu, nu, those actually, they give you like what we're looking for in the rest of this equation. So definitely very index heavy.
Yeah. So it's kind of in the current form it looks pretty implicit, because I'm kind of I want to see those permutations in the forms of the antisymmetric expression of the potential. So basically, in the equation above, we don't have the d mu a nu minus d nu a mu thing.
But we do.
It's not clear because you put the operators like in the separate brackets. It's kind of hard to see for me.
I see. So maybe it'd be easier to go from, I keep using a bunch of different colors here, but are you saying maybe it'd be easier to go from this equation?
Yeah. Because you already have that antisymmetry in the potential.
Mm-hmm. So this is actually, this is, you know how I mentioned that I got this from like the reverse of what people normally do. So now what we're looking through when we're like walking up this derivation backwards, this is the standard derivation that people do to show that the dual satisfies the Bianchi identity. It's like starting from this form with the Levi-Civita symbol, then you get this expression that we have written up there. And the reason that you get that is because it's still totally anti-symmetric. So we'd have that factor of 2 and all the minus sign terms, just you'd switch the indices and then we can cancel out the factor of 2. And then, so we're kind of like reading this derivation in reverse. But the point of me starting at the Bianchi identity and the definition of the field tensor was so that I can get the explicit form that Penrose writes down.
Yeah.
So, are there any other questions?
From this form or from this equation, is it apparent from here that the Hodge dual kind of changes the electric and magnetic fields to each other? Is the explanation somewhere here? Or I'm referring to the answer of my friend who says it's kind of the Hodge dual. It's kind of changing those fields, electric and magnetic fields, but via 2 forms. So I don't know if it's apparent here, or should it be treated from the other paper we were looking, the differential forms.
Well, go ahead.
Yeah. I just wanted to re-ask, are you asking about like why f is a 2 form, right?
no, actually, just from which equations is it possible to realize that the Hodge dual is such a thing that it changes the electric and magnetic fields to each other as two forms?
So you mean in terms of components, it's like switching magnetic and electric fields in the matrix?
Yeah, probably. Yeah. I'm supposing here that my friend gave me a correct intuition that it is similar to this process to like changing those fields, but I'm not sure if it's even correct. But
yeah, that is the right intuition. It's like to get the dual. What you can do is just anywhere that you see the electric field component, you replace it with the magnetic field component. And when you see a magnetic field component, you replace it with minus that electric field component. That is like one of the problems in this Griffiths book, is just to, replace, like do this substitution and then show that gives you the dual.
But okay. Then it's apparent from this your presentation also from the beginning there was this anti-symmetry part, like there. Oh, there. Yes.
Yeah. So the like another way to write. I gotta insert some space. So another way to write this is like oh, there we go. And I'll follow Chris's lead, but it would be gradient of phi minus dA dt. I missed this earlier. There was some time dependence that I missed, but it doesn't change. It doesn't change too much.
Yeah. So it's like more a space-time equation, right? Like where you include like x, y, z, and t also.
Mm-hmm. Yeah, so this there's a couple of steps to get from here. You need to apply some like continuity equation and stuff like that.
Maybe if it's a long derivation, we should go it on some other session then.
Yeah, I think so. I mean, the idea is that like the ith component of E will be like minus the ith derivative of phi minus the 0th derivative of A, and then the I component. So what we end up with from this sort of equation. Sorry, I need to reshuffle things so that it's in a nice order. So what we end up with from this equation and this definition of f is like f 0I is equal to EI. Because if we do like a 0th derivative of A, that gives us this term up here. And then when mu equals 0, A0 is just the phi component. So this is what I mean when like the first column of F is just the electric field. And similarly, we can actually do something with this boxed equation. I think it's star f 0 I is equal to minus b sub I. Or no, I think it's just b. I also think it's an upper. Oh, sweet. Chris is putting a lot of stuff in here. So Chris definitely worked this out more carefully than I am right now. But he's showing this like gradient of the scalar plus the time derivative of the vector, and the curl of the vector gives you the magnetic field, and he explicitly writes out the forward potential there. So yeah, this is all good stuff, Chris, and this is like exactly what we need here. So you can show that the first column of F is the electric field. You know, if you just look at the x, y, and z components, and the first column of the Hodge dual of F is the magnetic field components. So this is probably what your friend was talking about when he mentioned like, oh, you just need to switch electric and magnetic fields.
Yeah. Anyway, it was a lot of information, but I think this was a really good information to grasp more the Hodge dual. And what is Bianchi identity? Was it in our chapters what we just read? Because I just really didn't remember this at all.
Probably yes, in chapter 14 about curvature.
Okay. So it's some chapters back. Okay.
Yeah, so I propose like finishing up, and I want to make like a really small review for that, or create a plan for the next time. So basically, I want to talk about the article we haven't talked today. And I think that exactly that article can provide like more geometrical intuition about those like electromagnetic tensors, etc. So I mean this article about like pictorial introduction to differential geometry. And the point of view here for the n forms is kind of dual to the point of view which Chris uses in his videos, or was used in this article about using differential form in electromagnetic field theory teaching. Study in one moment. So basically, if you go to the bottom of that article, you will see more information. So you have a little bit more information than in the table from the previous article. So here we have had only like one forms degrees and dual vectors, scalars here. And here you can see that we also kind of explicitly see the relation between vector and the form. So for example, like E vector and E form, they are related with metric dual. And for example, D vector and D forms are related by metric dual or Hodge dual here. And also you can see that there is more information about the orientation. So we have those words like untwisted and twisted here. And those twisted and untwisted things is kind of connected with the definitions I talked about in the previous call, like pseudo-vectors. So twisted vector is a pseudo-vector, and maybe you have heard about pseudo-tensors. So pseudo-tensors, they are also kind of twisted tensors. And that's all connected with the orientation, and actually really greatly explained in that article. And also we have a table for the F tensor, for example, here, and like the information about the tensor in terms of the pullback, for example, on the space. It's kind of projecting on the space, and the remaining component, like the time component there. Yeah, so I think that it will be a kind of really logical continuation of our calls to continue with that paper and kind of finish with it, and afterwards just continue with the book. So we will talk, I think, like about 4D Maxwell equations and tensors using that article next time. Basically, that's the plan. I think it's a nice one. Sorry, pressed wrong button.
To me too.
Yeah, so
how many sessions we are going to have this year? Are you going to take the Christmas holiday break? And
yeah, one moment. I need to take a look at the calendar. I think that like the next time it will be like 12th of December and one more on 19th. And I think that's all. Yeah.
Yeah, it's good to have a small break.
Yeah. So we will have some holidays. I mean, like Christmas on 25th, right? And it's near 26th. So I think we should have some rest there. And also New Year on the like 1st of January and 2nd of January. So probably those 2 weeks will be for vacation, and that's kind of logical to have those for our heads to have some rest.
Right.
So I think that the next call will continue with kind of more geometrical intuition about those electromagnetic tensors and electromagnetism, and afterwards we'll just continue with the chapter.
So is it 19.3 or 4? What was the last chapter we went through?
I think the next one is 4, about gauge shifts for the potential.
Okay, curvature, yes.
Well, thanks for listening to my talk, everyone.
Yeah, thank you, Joe.
Right.
Thank you.
Thanks for
Good,
giving it.
good again. Yeah.
Yeah, I will post all the links to the articles in a beta chat, so you can kind of address those afterwards. Yeah, welcome Yuri, welcome everyone, and thank you all. See you next time.
Thank you very much. Yeah, have a nice week.
Yeah, bye, see you.
Bye, everyone.
See you. Bye.